Thank you very much, Sylvia, and thank you to all the organizers for setting up this great meeting. So I'm a second-year PhD student working with Julien Grain and Vincent Venin on quantum aspects of the early universe. And today I would like to present our work on cosmological master equations. So master equations are tools that come from quantum optics and that we want to implement in cosmology. But broadly speaking, my talk is about how do we do perturbation theory in cosmology when the quantum regime is relevant, such as it is the case during the early universe. I will first try to convince you that tools from quantum optics can be interesting for people doing gravitation and cosmology. Then I will present these so-called master equations. And finally, I will benchmark their efficiency on an exactly solvable cosmological model. Let me stress that these are preliminary results we should publish soon. So please, if you have any comment or question, I'll be extremely happy to discuss. But let's start from the beginning. To my mind, what is one of the most striking features of the standard model of cosmology is the ability to trace back the origin of all the structures we today observe in the universe, such as galaxies, clusters of galaxies, or the temperature anisotropies of the cosmic microwave background, to quantum fluctuations of the primordial vacuum that are stretched by the expansion of the universe during this period called inflation. It means that if we want to understand structure formation in cosmology, we need to master our understanding of quantum fluctuations in Kerr space. And this is something that has been widely studied in the simplest model of inflation, which is called single field swirl inflation. In this model, the early universe contains only one ingredient, the so-called inflaton, which is slowly rolling along its potential. And as long as it is slowly rolling, it will source the Einstein fields equation in a way that the universe undergoes a nearly exponential expansion, which is enough to set up the subsequent era of the universe and to seed structure formation. Now, despite the fact that single field swirl inflation is consistent with all the current observational data we have, any realistic attempt to describe the early universe in a wider picture usually relies on multi-field settings. It means that as early universe physicists, our role is to understand how a single field phenomenology could have emerged from multi-field settings, and what is the role of extra fields during inflation. And my talk will be mainly focused on this second point. In this presentation, we will adopt a very minimal approach based on three observations. The fact that single field swirl inflation provides a very good fit of the data, the fact that at some point inflation must end and connect to the physics of the standard model, and finally, the idea that if we want to embed inflation in a UV complete setting, we usually have to introduce new degrees of freedom. So the description that emerges from these three observations is the one of an effective single field system embedded in a wider environment made of degrees of freedom that don't play a significant role during inflation. And the fundamental question we ask is, what is the quantum description of this effective single field system? In fact, to answer this question, this is where quantum optics can be interesting. So far, I've told you about extra ingredient, but I didn't provide any concrete examples. So here is one, it's the case of a spectator field. In this figure, you have an inflationary potential for a two-field system where one direction is really flat, corresponding to single field swirl inflation, and the other one is highly curved, corresponding to a massive scalar field. There is this standard result from Wilsonian effective field theory, which is telling us that if we work at energy scale far below the mass of the heavy field, we can integrate it out, and the reduced dynamics is stabilized at the bottom of the inflationary valley, where at linear order in perturbation theory, the main result is just to have an effective speed of sound. Now, if I consider the same problem, but from another perspective, which is the one of open quantum system theory, I will realize that even if the light degrees of freedom barely interacts with the heavy one, it is usually enough to lead to quantum decoherence of the curvature perturbation. So to better understand this point, we need to develop what is this open quantum system approach. It's the idea that the full metasystem can be divided in two parts. The system, which is made of the degrees of freedom that we can measure, and the environment that we can't directly access. Since we don't directly access the environment, we want to integrate it out. And when we do so, the reduced dynamics of the system only becomes non-unitary, which means that it experiences two effects that are called dissipation and decoherence. The former is related to the energy exchange between the system and its environment, while the latter is due to the fact that when the system interacts with its environment, it gets entangled with it, which makes that some information is shared in a non-local form that can't be recovered by performing measurement on the system only. So what is our goal is to build an effective formalism which is able to encompass both the Wilsonian effective field theory results, but also the non-unitary dynamics from open quantum system theory. And to tackle this problem, quantum optics is interesting because in quantum optics, people are used to work on systems on which they perform measurement that are embedded in an environment that they don't know very well. For instance, they work in their room and they just know the room temperature. And even if it's something that they don't desire, the environment is always interacting with their system, which means that if they want to make reliable predictions on the observables of the system, they need to model the effect of the environment. And this can be made through different tools, but one of them is these so-called master equations. And our plan is to use this tool to describe this kind of setting in cosmology. So if this strategy is clear, I will now present what are these so-called master equations. In fact, being a cosmologist, the fundamental objects I'm interested in are the correlators, the endpoint function of the theory. And if I want to compute them in a quantum framework, I usually need an object which is called the quantum state of the system, or the reduced density matrix. And in fact, a master equation is nothing but a dynamical equation for this quantum state. Now, what I would like you to remember of this presentation is that there is no such thing as one master equation. It's more like a whole bestiary depending on the level of approximation you work at. For instance, there exists an exact master equation, which is just a recasting of the exact dynamics, focusing on the degrees of freedom of the system. The problem is that it is as difficult to solve as the full original problem, and it relies on a perfect understanding of what is the environment. So to simplify the problem, you can start to perform approximation. And there are mainly of two classes. The first one is related to the way the system is coupled to its environment. And the second one is related to the nature of the environment itself. So let's start with the first class of approximation, the so-called Born approximation. Usually, the system is weakly coupled to its environment, because otherwise the mixing would be strong and we couldn't distinguish anymore the system from its environment. So what we can do is to expand the exact dynamics in powers of the coupling constant between the system and its environment. And if this coupling constant J is small enough, we can hope to truncate this expansion at some order so that we will just solve for the few first powers of the coupling constant. When I do so, I don't perform any approximation on the nature of the environment itself, which can be, in general, out of equilibrium. Now, if I have some information on what is my environment, I can go one step further and, for instance, performing the so-called Markov approximation. It comes into play when your environment is made of a large collection of degrees of freedom that are interacting so that they form a thermal bath. And if the environment is a thermal bath, it means that the correlations are short-lived in it, so that the environment is not able to keep track of the past interaction with the system. So in this limit, we can derive a Markovian master equation, which is well known under the name of GKSL or Lindblad equation, which has a very interesting mathematical structure, which is extremely useful. Now, the question we ask is, where should we work in cosmology? What is the good level of approximation when you work in curve space? And in fact, this is not trivial. In quantum optics, the Markovian master equations are ubiquitous because the environments are almost every time large, stationary, and at thermal equilibrium. But if we work in cosmology or in curve space in general, we need to be careful and to reassess these approximations. Because in curve space, the background is curved. In cosmology, it is symmetric and dynamical. We don't have, in general, an asymptotic state in the future boundary. And the environments in cosmology can be out of equilibrium. So my point here is to say that even if master equations have already been applied in cosmology, as you can see in these references, we have to remember that they were designed in a very specific context, and we have to be careful when we want to apply them in curve space. In particular, we have to reassess the approximation schemes and the regimes of validity. This is why with my supervisor, we benchmark this master equation program on an exactly solvable model, so that we have a perfect analytic control on the dynamics, and we are able to say if the master equation is doing well or not. So if this point is clear, I will finally end my presentation with presenting the model on which we benchmark this master equation. It's the so-called curve space Caldeira-Leggett model, and it's simply made of two massive scalar fields that are linearly coupled in a de Sitter background. These fields are called test fields, which means that they don't backreact on the geometry, which is treated classically. We take one of the fields to be light, which will be our system that we will probe, and the other one is really heavy, so that we will integrate it out, and it will constitute our environment. As you can see, the interaction is linear, so we can exactly solve this problem by, for instance, performing a rotation in field space so that we solve the problem in the mass eigenstates. And also, as you can see, it's a Gaussian system, which means that all the information is contained in the two-point function of the system. And in particular, the quantum information properties, such as, for instance, the purity, which in this case is equivalent to a measure of the level of entanglement between the system and its environment, is also connected to the two-point function of the system. So now that we have given an exact description of this very simple model, it's time to integrate out the heavy field and look at the effective description obtained by a master equation. So if I integrate out the heavy field, I obtain this kind of master equation in the Fock space. You can see that it's a dynamical equation for the quantum state of the system. It has a unitary part which contains the free Hamiltonian and the so-called long-shift Hamiltonian, whose role is to renormalize the parameter of the free theory, on the top of which we have also a non-unitary part. And this non-unitary part is a bit hard to interpret in the Fock space. So we can map this equation in the phase space in terms of the reduced Wigner function, and it takes the form of a maybe more familiar Fokker-Planck equation. And as you can see, in the phase space, we observe that the non-unitary part contains two terms. The first one looks like a drift term, so it's really an energy exchange between the system and its environment. This is the role of dissipation. And the second term looked like a diffusion term, which is related to the spreading of the Wigner function. And this is usually related to the process of quantum decoherence. So now that we have described our reduced problem thanks to a master equation, we can use it to derive, for instance, the so-called transport equation, which are the dynamical equation for the observables of the system. And the final question of this problem is, how do we solve it? In fact, the master equation have been studied in cosmology for their ability to resum late-time secular effects. And what we realize is that to perform this resummation, we need to solve this transport equation non-perturbatively, taking the master equation as a bona fide dynamical map. If you want, in spirit, it's the same thing as when you derive an effective field theory, you obtain an effective Lagrangian, and then your effective Lagrangian is the starting point of your new theory. Here, it's pretty much the same idea, but focusing on the dynamical equation of the quantum state of the system. So now that we have solved our problem using the master equation, it's time to benchmark it. And if we want to benchmark it, we need to compare it with some other techniques. So we decided to compare it with standard perturbation theory, which is just the expansion at a given order of the coupling constant between the system and the environment of the exact results. And the two things we investigate is the accuracy on the two-point function, so on the observables on the system, and the ability to recover quantum information properties through the purity. So in the minute remaining, let me show you the results. In this figure, you have the relative error on the 3 and 3 of the covariance matrix for different values of the coupling constant between the system and its environment for both the master equation and standard perturbation theory. And what we observe is that thanks to the resummation performed by the master equation, we have a strong improvement on the precision we compute the observables. For the parameters investigated in this figure, the improvement is at least of 2 orders of magnitude, but it can be much more depending on the observables you look at. So if you want to improve the accuracy on the observables you are computing, you can use the master equation so that it will lead to a resummation. Now, if I look at the quantum information properties, in this figure, we have the purity and its relative error as a function of the number of e-folds after Hubble crossing. And what we observe is that the master equation is able to keep track of the quantum information properties even in the fully decohered regime, while standard perturbation theory is not able to keep track of this information when we leave the nearly coherent regime. As you can see, the stability of the error is an example of late-time resummation performed by the master equation. So let me wrap up what I've told you in this presentation. I said that in cosmology, we need to deal with elusive environments, which means that effective field theory and open quantum system are interesting to separate things we know from things we don't. The master equation program may allow us to go beyond standard perturbation theory, but if we want to use it in curve space, we need to reassess its approximation schemes and regime of validity. This is why we benchmark this program in an integrable model, and what we observed is an improved precision on the system covariance and the ability to recover quantum information properties. So now there are a lot of directions we would like to investigate in the future, but to my mind, what is one of the most promising one is to apply the same kind of analysis to a nonlinear theory, so that ultimately we will be able to connect observational signatures such as primordial non-Gaussianities to quantum information theory, such as quantum decoherence of the curvature of perturbations. So to my mind, I hope that one day, if we better characterize the imprint of the hidden universe on observable cosmology, we may be able to reveal its nature. So on this word, I thank you for your attention, and please, if you have any question, I'll be happy to discuss.
Okay, thank you for your very interesting talk. Now it's time for questions in the audience. Do you have any question or comment or? Okay, Gerardo.
Hi, thank you for this wonderful talk. I'm curious because I've always thought that this Born approximation on the one hand and the Markov approximations are to some extent very intertwined, and it's very hard to disentangle them. So could you comment on how can you distinguish, like how can you break explicitly that?
Yes, I think that the two are really intertwined in the case where you want to work in a Markovian framework. So you want to derive a Lindblad equation. And I agree that when I start to work on this topic, for me, it was really difficult to disentangle the two. Maybe I have some backup slide that will help to better explain this. So in fact, it becomes easier when you consider the fact that you can have a non-Markovian master equation. And the first thing you do is to, this is just a rewriting of the exact dynamics, okay, where you write the evolution of the reduced density matrix as a convolution of the so-called memory kernel, okay? And this complicated object, the memory kernel, depend both on the coupling of the system with its environment and the nature of the environment itself. And as you can see, this process is fully non-Markovian. At the time it's exact, we don't have made any approximation, and it's non-Markovian is the same in the sense that we need to convolve it in all the past history up to the initial time of the interaction. And if you want to disentangle the two classes of approximation, you can start to work with this approximation and first say, okay, the first thing I will do is to expand this object in the coupling constant between the system and the environment. And when you do so, the only approximation is a weak coupling between the system and this environment. And you will obtain a whole class of master equations that are called the time convolution-less master equations. And the only approximation when you derive them is just a weak coupling between the system and the environment. And this is, in fact, when you do so, I think it's good because it's helpful to understand where the two approximations enter into account. So you first perform this weak coupling approximation, and when you are done, you still have to make this convolution over the past history, which means that it's a non-Markovian master equation. And this is where the Markov approximation enters into account. The Markov approximation will tell you that, maybe it's clear here, that your memory kernel is sharply peaked, so that in this case, you can approximate the convolution by just looking at the thin slice, which is local in time. And this is where the Markovian approximation enters into account. So,
but aren't you making also another approximation in which you essentially factorize the density matrix? You assume that that holds for all times. That's another approximation, right?
No, because we make the approximation that at initial time we don't have any correlations between the system and its environment, so we start with a factorized density matrix. But after, the fact that you can have correlations enters into account is just that when you do the power counting order by order in perturbation theory in the coupling constant between the system and its environment, you will see that the correlations, the part of the density matrix that can't be written in as a product state is always coming in with a higher order in the coupling constant. So this is why this way to organize the master equation holds. Does it make sense? Or we can further discuss later on if, because I have the feeling that was not perfectly clear on this kind of thing. So if you want to discuss later on, it's possible.
Sure, sure. Thank you for your answer. It was very illustrative. Yeah.
Thanks.
Okay, so there is another question in the chat. Well, first, thank you for the nice talk. It's from Jose de Ramon. And then the question is, can you explain how you solve the equation numerically? Is it a PDA?
Yes, thank you for the question. So far, we are trying to improve our numerical scheme because it can be improved. So as you can see, it's rather an ordinary differential equation for the two-point function of the covariance matrix. And it's not too difficult to solve because the transport equation is like that. You can either solve it numerically the same way you solve an ordinary differential equation, or you can use an analytical solution, which is this form. So you can see that there exists an analytical solution, but you also need to perform some numerical integration at some point. And the idea is pretty much the following. If you want, when you integrate this differential equation, you observe that there are mainly three effects. The first one is the unitary effect. So since it's unitary and we work with a linear system, we can solve it using a green function. So here you have the evolution thanks to the unitary dynamics. You have a damping term, which is coming from the dissipation, okay? And finally, you have the diffusion is playing the role of a source term, so we need to convolve the source term with the Green's function. So you can, in the end, my answer is that you can either solve the ordinary differential equation numerically, or you can use this analytical solution, but you still have to perform some numerical integration. And now to end the project, we are trying to figure out what is the most optimal way to deal with it numerically.